Hello everyone, and welcome to another episode on Arbitrary Precision Arithmetic. So today we're going to be covering the long division algorithm. Now, what is long division? From the name it's quite clear that it's some kind of division algorithm, and because we're doing arbitrary precision integer arithmetic, this basically means we want to divide two arbitrary precision integers. Now this algorithm is basically equivalent to the algorithm that's often taught to school children for division, and this is also sometimes called long division. So if you know that, then it should be easier to understand this topic. However, I'll go through the algorithm anyway. Now, this algorithm has a time complexity of O(n) squared. If you don't understand what time complexity is, just click on the video, what is time complexity, it should appear right now. So that being said, this is an algorithm for division in our arbitrary precision arithmetic system. So how do we actually divide with only integers? Now, when we are doing division, when we divide two integers by each other, normally when we're doing normal maths, just thinking what is 10 divided by 3, for example, well, we would say it's 3 1/3 or 3.333 recurring, and this is clearly not an integer. So we want to avoid getting a rational number as a result. So how do we do this? Well, what we actually do is we split the answer into two parts, the quotient and the remainder. The quotient is the integer part of the answer. So in this example, 10 divided by 3, we have 3 1/3, and 3 is the integer in this, so we say the quotient is 3. When you divide a number into different parts, so say we have 10 cake slices, and we're splitting it between 3 people. We give each of them 3. The remainder is what's left. So if you give 3, 3, 3, you will have 1 cake slice left. And this is equivalent to the numerator of the fraction that we have here. So that's 3 1/3. Now let's go into an example of actually applying this with decimal numbers. So this is our decimal example of the long division algorithm, and here what we're doing is we are dividing 883,474 by 227. Now, we'll go over some terminology in case you aren't familiar. The number that is to be divided is called the dividend, and this is going to be divided by the divisor. So we are dividing the dividend by the divisor. Now, the number that we want to find, well, we have two numbers that we want to find. One of them is the quotient and the other one is the remainder, and the quotient goes above the dividend in this notation. There are other notations, but this is the one that we're going to be using. And the remainder goes somewhere underneath the dividend. We'll find out where exactly as we do the calculation. Now, what are we actually doing in the long division algorithm? Well, essentially, we are trying to find each individual digit of the quotient step by step. So we want to find each digit, and how we do this is we first off start by taking a chunk of the dividend to find the first digit. This chunk has to be small enough to give us a single digit for the quotient. So in order to be guaranteed to have only one digit in the division, we need the dividend to have the same length as the divisor. So just taking the first digit, 8, this is going to be 0 when we divide it by 227. This is going to be useless. We know it's definitely going to be 0. in more general terms, any division where the dividend has fewer digits than the divisor will just give you a quotient of 0. So 883 are the first 3 digits of the dividend. This is the smallest number of digits that will possibly give us a quotient that isn't 0. And it's also guaranteed to give us a single digit as the quotient. So this is the first step. We divide this section of the dividend, which we call our intermediate dividend, by the divisor. So we are doing 883 divided by 227. Now, how do we actually do this division? How do we find the quotient in a division? The quotient is essentially the greatest number that will multiply by the divisor to create a multiple that is smaller than the dividend. So we want to find the greatest number that multiplies by 227 to create a multiple that is less than 883. Now, in order to determine which number this is, in this case, we have constructed a multiplication table. As you can see on the right hand side of the screen, in the first column of this table, we have the digits that we are multiplying by the divisor, so these are the possible quotients. And on the right hand side, we have the multiples of these numbers and the divisor. Now let's just start. So what is the greatest multiple of 227 that is still smaller than 883? If we go through the table, we will see, so it's not 2043 because that's greater than 883. It's not 1816 because that's also greater than 883. This is also greater than 883. So we keep going down until we find that this is the biggest multiple of 227 that is less than 883, 681. And we obtain this by multiplying 3 by 227. So the first digit of our quotient is 3. And now we need to calculate the remainder of this smaller division that we're doing, 883 divided by 227. So what we do to calculate the remainder is we subtract the multiple that is less than 883 from 883, our intermediate dividend. So once we subtract them, this will give us 202. Now we're not done, since we still have to find the remaining digits of the quotient. In order to obtain the next digit, we need to continue with the division. So we start one digit at a time, we take the next digit of the dividend, and we add this to the end of our remainder, and this will give us our new intermediate dividend. And then we just repeat the same thing we did before. What is the greatest multiple of the divisor that is still smaller than 2024? And if we look at the table, we will see that this is 1816. And we obtain this by multiplying the divisor by 8. So we now know that the quotient's next digit is 8, and we will write the multiple that we got, 1816, and subtract this from the intermediate dividend to get our new remainder. which we find to be 208. And then we continue the same process again. We take this 7, the next digit of the dividend, down to get our new intermediate dividend. We find the greatest multiple of the divisor that is smaller than it, and we find that this is 2043. And this is obtained from 9 multiplied by 227, so 9 is our next digit of the quotient. And then we subtract the multiple again to get the new remainder, and this is 44. Then we carry the final digit of the dividend down, and this gives us 444. And we look for our next quotient, and it turns out that this is 1, and this gives us the multiple 227. So we write that our quotient is 1, and we take our remainder, subtract 444 minus 227, and this is 217. So we have reached the end of our division. So this is actually our final remainder, 217. This is the remainder of the entire division, and the quotient on top is our final quotient. So we can say that the result of the division, 883,474 divided by 227 is equal to 3,891 remainder, and I will write R for remainder here, 217. So this should be the correct answer. Now that you have seen the process done in decimal digits, let's see how we can generalize this to an arbitrary base. So now we're going to be looking at the algorithm expanded for an arbitrary base. So on the left hand side of the screen we have the first step, we're going to have the step that we're currently looking at, and on the right hand side we have an example of each step so that it's easier for you to visualize it. Now the first step is, if the dividend has fewer digits than the divisor, the quotient is 0 and the remainder is the dividend, and the algorithm ends. So we went over this a bit at the start of the decimal algorithm, and it turns out that if the dividend has fewer digits than the divisor, the dividend is guaranteed to be less than the divisor. So there is absolutely no way that you can get a multiple of the divisor that is greater than 0, but that is also less than the dividend. Now, in our example here we have 57 divided by 120, and this just gives us 0 remainder 57. Now the next step, step 2. Otherwise, so if it isn't the case that the dividend has fewer digits than the divisor, we initialize the remainder to the L-1 most significant digits of the dividend, where L is the amount of digits in the divisor. Now basically what this means is we are initializing the remainder to the first few digits of the dividend, and this doesn't seem to make a lot of sense at the moment, probably, but we will see how it makes more sense later. And the amount of digits that we're setting it to is 1 less than the amount of digits in the divisor. So we'll see how this makes sense later. Now, step 3, we initialize the iterator I to 0, so we're beginning to go into our iteration, iterating through each digit of the dividend. Now, step 4, set the intermediate dividend to the remainder. plus L plus ith digit of the dividend. And when I say plus, I'm talking about concatenation, not addition. I mean just slapping the digit back on the end of the remainder, not arithmetically adding them. So now we can see our remainder was the first two digits of the dividend in this example, 88, and when we add the next digit to the end of it, we get 883, which is our intermediate dividend. So the second step should make some more sense now. We are just making it so that we can do this addition of digits each iteration without having to initialize the intermediate dividend before the iteration starts. So, step 5. Find the next digit of the quotient using a binary search. The next digit of the quotient is the greatest multiple of the divisor less than the intermediate dividend. Now, why do we use a binary search? So first of all, if you don't know what a binary search is, I will just explain it quite simply here. Basically, when you make a binary search, you're searching for a value, and the way that you do it is you use two bounds. You use an upper bound and a lower bound, and these are essentially the range which your answer is guaranteed to be within. And within the binary search, you keep halving your bounds. You keep halving the distance between your bounds. You keep narrowing the bounds down until you reach the actual answer, until you reach a single number. That's explained very simply. Anyway, the reason that we use a binary search instead of a table, a multiplication table like we did in the decimal example, is that a binary search is a lot easier to do than searching through an entire table when you get to higher bases. So in our code example that we're going to show later in this video, the base is 2 to the power of 30, so you have 2 to the power of 30 possible digits that could be the possible quotient. Now, if you construct a table of the size 2 to the power of 30, that's going to take up a lot of memory. So what's that? That is a ridiculous amount of memory. Essentially, you're going to use up all of your RAM, so it's impossible to do that with a table once you get to massive bases. So the binary search algorithm is a way that we can search for what the correct quotient is. Now, the next digit of the quotient is the greatest multiple of the divisor less than ID, and this is just our condition that we are giving to the binary search algorithm to find the actual quotient. And we went over this a lot in the decimal example. Now, step 6. Calculate the new remainder by subtracting the product of the quotient digit and the divisor from the dividend. Now, this is what we did at the end of each iteration. We just calculate the remainder. It's the same for any arbitrary base. You just do the same subtraction. It's the same. Now, step 7. If I is less than or equal to k minus l, increment I can go to step 4, and k is the amount of digits in the dividend, and L is the amount of digits in the divisor. So this is basically just giving our iteration a limit of the difference between the digits in the divisor and the digits in the dividend. And this is because the only digits that we're iterating through are the last few digits after the first intermediate dividend. So if the initial intermediate dividend has the same amount of digits as the divisor, then the remaining digits that we're actually iterating through is just the digits in the dividend minus the digits in the divisor. So again, to reiterate, this is reiterating. This is going back to the start of the iteration if we have to. And once we've reached the end of the entire loop, the algorithm ends. We now have the correct values for the quotient and the remainder. And as you can see on the right hand side, the same as the completed long division algorithm that we did before. Now this is just the algorithm laid out fully. This is the full algorithm. You can take notes, you can pause the video if you want to read this again, but we are going to be looking at an actual implementation of this in our Python demonstration. So now we're going to have a look at our Python demonstration of this algorithm. All of this code can be downloaded from my GitHub. It's public domain code. I don't care whatever you use it for, just download it. I'll put the link in my description. And anyway, off we go. So we have our class biguint. Our base is 2 to the power of 30 as we are setting at the start, just as a reminder. Now, there are two new methods that I've added. The first method isn't really related to division. This is just a method that I added to clear up some stuff, to fix some issues that were occurring before. So this method is called normalize, and what this does is it strips zeros from the beginning of a number, from the most significant digits of a number. And this is because having leading zeros at the start of a number can cause issues with when you're comparing the size with other numbers. So think, for example, when you're comparing 002 to 5, for example. So if you think about the comparison algorithm, if a number has more digits than another number, then the comparison algorithm will determine that it is greater than that number. Now, if we have leading zeros, these are real digits. They're actual digits in the list of digits. So if we compare 002 to 5, we will see, okay, 002 has 3 digits and 5 has 1 digit, so 002 must be greater than 5. However, this isn't the case, of course, because 2 is less than 5. So we have to strip the zeros from the most significant positions of the number. We have to strip the leading zeros, and this is what this method does. It removes the issues that were occurring before if you go back to the previous episodes, but this is a very simple function. It's just a while loop. It just strips each zero from the most significant parts and then sets the new number to this. So yeah, that's that. Not really related to the division algorithm directly, but just important that you know. Now here we have the division algorithm. So we are taking one parameter, the divisor, and this method will return a tuple of both the quotient and the remainder. So, of course, in the algorithm we calculate both the quotient and the remainder, and we return both of them. So first I'm just setting some aliases, I guess. We're setting A to the digits of the dividend, and we're setting B to the digits of the divisor, so that it's shorter to refer to them, so we don't have this very long code like len self.digits is less than len divisor.digits. It's just quicker to do this. Now, we initialize a few things. We initialize the digits of the quotient, the remainder, and these are empty lists, which means that they're equal to 0. And we initialize the intermediate dividend also to 0. Now, we go on to step 1 of the actual algorithm. So step 1, if the length of the dividend, the amount of digits in the dividend, is less than the length of the divisor digits, then the quotient is 0 and the remainder is the same as the first number. So remainder digits is equal to the dividend digits. And as we've already set the quotient to 0, to just this empty list, we have our answer in this case. And after this if statement, it just executes this, it just makes a tuple of the quotient and remainder, normalizes them, and returns them. So that's our first step. Our second step is to initialize the intermediate remainder, and then begin iterating after this, but that's not this step. So step 2, if the length of our divisor is greater than or equal to 2, we set the remainder digits to the last few digits of the dividend, and the amount of digits is equal to the length of the divisor digits minus 1, and it's made negative since it's the last digits. And the reason it's the last digits in this case instead of the first digits is because this is actually little endian. We have the most significant digits at the end and the least significant digits at the start. And the reason we have this condition, the if length of the divisor is greater than or equal to 2, well, if you remember how many digits we have, it's the amount of digits in the divisor minus 1. So if it's less than 2, if it's just 1 digit, then we have 0 digits in our initialized remainder, so this doesn't do anything otherwise. So we're just checking if the length is greater than or equal to 2. Now we go on to step 3, step 3 and 4. So step 3 is to begin the iteration. We're initializing I, and we're setting it to 0. And in the last step of the iteration, which is step 7, I think, if I remember correctly, the condition for the iteration ending is if the iterator I is greater than the length of the dividend minus the length of the divisor. So that's just this here. So this is our range, 0 to the length of the dividend minus the length of the divisor, and plus 1 because it's not inclusive in Python. Now, step 4, we add the next digit of the dividend to the intermediate dividend. So intermediate dividend is equal to a new big uint, which is 0 plus the remainder digits. So this is just us adding a new blank digit onto the end of the remainder digits, and then we add to this the next digit of the dividend, and this is calculated by this. And that's how we do a concatenation. We could just add this to here, but for some reason I decided not to do that. I wanted to make it more complicated. I don't know what I was thinking. But you can simplify that if you want. Anyway, the next step is find the next digit of the quotient using a binary search. And the next digit of the quotient is equal to the greatest multiple of the divisor less than the intermediate dividend. So this is the actual binary search algorithm. We are setting min q, which is minimum quotient, to 0, and the maximum quotient is the base minus 1. So those are like I described before, those are the bounds for the digits that we initialize. So the smallest possible digit that we can have as the quotient is 0, and the greatest possible digit that we can have as the quotient is the base minus 1. So then we actually do the binary search. And also before that we set q next to none, and the next is just the guess for the quotient. We do the binary search while the lower bound is less than the greater bound, or the upper bound. We get the next guess of the quotient is in the middle of the last two. If you're familiar with the binary search algorithm, this is what you do. This is how you actually make a guess. You guess in the middle of the two bounds, and we're doing this using an add and a shift. So that's how we get to the middle of these two bounds. Then we compare the intermediate dividend and the guess for the greatest multiple of the divisor less than the intermediate dividend. Now what that means is we are basically checking if our guess is correct. We're checking if the guess is less than, equal to, or greater than the actual intermediate dividend. Now, if the comparison equals 1, which means if the intermediate dividend is greater than the multiple of our guess, then we are setting the lower bound to the next, to our guess plus 1. So we are just shifting up our guess if the guess is too small. So the opposite thing happens if our guess is too big. We shift the bound downwards. And then otherwise, if the guess is exactly equal to the dividend, we have an exact perfect division. So we just end the binary search. And this is just the thing that accounts for divisions with a remainder. If we don't exit through this condition, then we actually end up not doing an extra one of these. So we need to do, we need to make our guess in the middle of our new bounds at the end. And this will give us the correct answer for the quotient digit. And then we calculate the remainder by simply subtracting the multiple of the divisor and our guess for the quotient from the intermediate dividend. And then we set the quotient digits to the next quotient digit plus the quotient digits from before. So we're just concatenating the next quotient digit to the original quotient digits. And then we restart the iteration if we have to, go to the next digit, or we end the iteration and return the answer. So this sums it up for the explanation of long division. So we can just quickly go through some examples now. Now, we have this in the same folder as the actual algorithm, so you can also download these examples from my GitHub, and you can try out your own examples. Feel free to play around with this, just to check that it works. And once we run this, we see, first of all, we have x is equal to this number, and y is equal to this bigger number. Now, since this number is bigger than this number, since the divisor is bigger than the dividend, we know that the quotient will be 0 and the remainder will be the same as the dividend. So this is correct. Now the next division we have is 79 and a ton of zeros divided by 79. Now this should be 1 and a ton of zeros, and with a remainder of 0. So this works. This is a correct division, probably, if this is the same amount of zeros. Now, the next one, we have a similar division, 79 with a ton of zeros divided by 1 with a ton of zeros, and this is 79,000, remainder 0. This should be correct as well. And we have another division where these two numbers probably have the same amount of digits, and we are just showing that even if they have the same amount of digits, it still works to find that the remainder is the dividend and the quotient is 0. So those are our examples. If you enjoyed this video, if this helped you, then please drop a like, leave a comment, and subscribe, hit the bell. Always helps me, it'll help with the YouTube algorithm. Way more complicated than this long division algorithm, but it will help. And yeah, if you want the code, just go into the description, it's on my GitHub. I upload every single episode's code from onto here, but this episode 6, long division, this will be the most recent, so this will be the best code. And so, see you in the next video.